Scientific American's 60-Second Science. I'm Emily Schwing. Have you ever looked up to see a hawk soar overhead? Or a small chickadee flit by and wondered, how do they do that? Believe it or not, scientists never really knew either until now.
I looked at the relationship between form and function in the most basic sense.
Talia Lowy-Mary is a PhD student at the University of Toronto in Canada. She says bird flight has everything to do with the shape and size of a bird's sternum or breastbone. Bird sternums have a projection from the middle called the keel, and this is where the flight muscles are attached.
It's plausible to think that this element is important for flight, but why does it vary so much in shape and size relative to the body? There are all these questions about it that haven't been answered in the past.
So Mary set out to find some answers using a database of CT scanned sternums from 105 different bird species, like the red-capped lark, Leach's storm petrel, and the southern cassowary. She also included 2 extinct birds, the dodo and the great auk. The scans combine a series of X-rays to create 3-dimensional images.
And so because the sternum is a complex element in 3 dimensions, it's not just a 2D bone, it's got projections out the middle and out the sides. Looking at it in 3 dimensions is the best way to quantify the shape and analyze it in a statistical framework. So more recently, those methods have become more accessible. And I guess because of that, I was able to do it now. And maybe 10 or 15 years ago, it wasn't possible.
Mary and colleagues used the scans to create computerized 3D models.
And so when you do that, you can move it around, you can place points on it in the important spots. And so that's what I was doing. I was putting these dots that are called landmarks. And the landmarks basically quantify in 3D computer space where the important points are on the element.
The findings published in BMC Biology show that sternum size and shape has a direct impact on the way a bird flies.
So an eagle would be soaring and wouldn't be moving its wings as much. It just has its arms stretched out. It has very intricate structures in its wings and in its shoulder to hold the wings out, but it doesn't have to use as much flapping power.
But compare the majestic eagle with a frantically flapping duck. Birds with a deep sternal keel fly more slowly. Those with long sternums are associated with running birds. Mary also looked at foot-propelled underwater diving birds. These are species like the cormorant, the loon, and the grebe.
They have this streamlined sternum with a lower sternal keel, so everything is kind of compact and flattened. But you actually see something really similar in birds that are wing-propelled divers.
Those wing-propelled divers include small birds you might find on the ocean, puffins, common murres, and penguins. Mary says whether wing or foot-propelled, the sternums of these birds are similar in shape.
All other sorts of factors are possibly, most likely, contributing to the shape of the sternum, not just locomotion. Things like birds that dance to attract a mate, or how big their egg is relative to their body size. There are all sorts of things that could be contributing to this. We've just, scratched the surface, looked at one aspect of variation, but there's so much more.
Mary believes that the shape and structure of the sternum impacts how different species of birds breathe. She also says different methods of flight mean different resource demands for individual species. Diving deep into how birds fly today can tell scientists a lot about how they evolved over millions of years.
So birds evolved from dinosaurs, and we don't know exactly which fossil birds and which dinosaurs were capable of flight, but gaining a better understanding of how birds fly today is the key to completing that picture of how the dinosaurs were moving through the world.
Mary plans to dig into fossil birds next, in part to learn more about the origins of flight.
the thing about fossil birds is that a lot of them are flattened into rock slabs, but there are so many amazing bird fossils, especially from China. And so they will have to be studied a little bit differently because I may not be able to put them in a three-dimensional context as I did with the modern bird sterna.
For now, though, she says she's looking differently at the small passerine birds that flit by her windows and dominate the tree branches in her backyard in Ontario.
They're mostly continuous flapping birds. They're flapping pretty quickly. They're moving from branch to branch. You know, they're trying to keep away from predators and get some food, whether it's insects or berries. Yeah, it made me think about how, you know, their skeletons are structured and also how their muscles are working much differently than, let's say, a hawk that's soaring above. And so they would require different metabolism and different food sources, and how they use that in their body would be very different.
For 60-second science,
OK， 这个刚开始还讲说，因为甚至到现在，他们也都不科学家都不知道鸟怎么飞，所以他就拿 X 光扫描很多种类的鸟，然后去把它输入到电脑里面，然后去模拟它的那个模拟它飞的感觉，就是模拟那个形状对。然后他后来有比较说哪一种鸟飞起来怎么样，像是他比较那个 eagle 跟一种 bird， 然后就什么飞得比较用力怎么样，但是其实它们结构跟飞起来都差不多，然后差不多吧，差不多是这样，后面对差不多。
这边主要是在研究关于鸟类的一些结构上的差别，然后他们就有说到说，像是说他们有用各种去仪器去观测很多种，大概他好像说150种吧的鸟类的那个每个鸟类的结构构造啊之类的，然后他们也有说到说，他们除了观察以外，他们也有观察过各种的鸟类，像是在水里的鸟类啊之类的啊。然后呢，他们就有说过，不管是在水上还是在空中，然后或是飞得很快的，基本上他们的就是有一种骨架那种感觉都是差不多的。然后再来，他们最后就有说到说关于他们的演化的部分，对。